All right, welcome everybody to our TUM AI Lecture Series. It's a pleasure to have Saining Xie here today. He received his PhD and master degree from UC San Diego. After graduation, he joined Facebook AI Research Fair as a research scientist. After a few years of working there, he then moved on and became an assistant professor at NYU, where he is still right now. He has then built one of the most renowned and leading groups in computer vision and machine learning today. And of course, many of Saining's works is widely known in the research community. It includes a lot of representation learning, works around transformers, and many of these works have been part of every modern ML course already, talking things like MoCo, masked autoencoders, and very recently, diffusion transformers have gained a lot of attention too. So it's a real pleasure to have such an outstanding researcher here with us today, and we're looking forward to what you're talking about.
All right. Okay. Yeah. Thank you so much, Matthias, for this kind introduction. I'm really glad to be here. And today I'm going to talk about the multimodal future and why scalable representations still matter. My name is Saining Xie. I'm currently at NYU right now. Yeah, let's just get started. So multimodal learning, especially vision language model, is a very popular area in AI right now. So there's lots of labs, both academic and industrial, exploring it, right? There's like new ideas and innovations every day. But in this talk, actually, I'll cover some of our work from the last 2 years since I joined NYU. But we'll also look ahead and discuss future directions. But before that, I want to just take a quick step back and think about how things were in visual understanding, in representation learning before multimodal learning or even large language model became a thing, right? And by the way, if you have questions, I know this is kind of live streaming and Zoom meeting, but feel free to just jump in and ask, especially clarifying questions. Okay, and this slide I just want to show humans are incredible good at building internal biological and cognitive representations. And usually this is done super quickly and without we even realizing it. We depend on these representations to handle everyday tasks. And I would say similarly for AI systems, we also need to build useful representations, internal representations, to perform well on classification and other prediction tasks. As I said, a few years ago, we're still in this supervised learning regime. And in supervised learning for vision tasks, we really learn a mapping directly from the data to the categorical labels using neural networks. And now, it's clear this is definitely a very limited approach. For example, under pure supervised learning setup, generalization is really a big issue there, right? The network might look for spurious correlations or just memorize everything, which is not ideal. So at that time, I think, we have this new thing called self-supervised learning, right? The goal for self-supervised learning is to explore the structured information there in the data and to build sort of background knowledge to approximate a form of common sense in AI system. And in traditional visual self-supervised learning, we typically pre-train a model using some carefully designed pretext tasks. And after pre-training, we evaluate the model using either linear probing or end-to-end fine-tuning on standard recognition tasks, such as classification or detection. So over the years, we have developed numerous SSL techniques, including contrastive-based methods and masked autoencoder-based pretext tasks. And we have extended these approaches beyond just 2D pixels and images to include videos and 3D point clouds. So if you ask me whether we've succeeded, right, my answer could be yes. So SSL-based visual representations can indeed surpass many traditional supervised pre-training baselines on many benchmarks, achieving state-of-the-art performance across the board. But if you ask me again, my answer probably will be no. And SSL-based visual representations haven't scaled effectively. Or perhaps we just haven't yet discovered the right recipe for scaling them. And to be honest, we have limited success over the recent years. And now we all know the large language models and next token prediction scale exceptionally well for language representations. However, my hope is by the end of this talk, I can convince you that relying solely on scalable language representations isn't sufficient. So I'm sure many of you here are very familiar with this parable of the blind man and the elephant. So to me, I think large language models are kind of similar, right? They possess extensive knowledge about the world, but they are essentially kind of blindfolded. And while language captures a great deal of the information about the word distribution, there are numerous kind of scenarios where it's actually crucial for this knowledge to be grounded in more kind of objective, more comprehensive, more kind of sensory experience. And this is why over the years people are, we're gaining a lot of interest in this multimodal large language models, and people say, oh, this is like the dawn of large multimodal models, and people use the 2B4V model to explore all this diverse visual understanding tasks across many, different domains. But with all this kind of perspectives, I still want to argue we need better sensory representations, and only having good language representation is not enough. So I'm just quoting my colleague at NYU, Yang Kun, and his two quotes I find extremely relevant here. It says most of human knowledge and almost all animal knowledge comes from our sensory experience of the physical world. And also language is the icing on the cake, and we need the cake to support the icing. This is like LeCun's famous cake analogy, maybe 2.0. But what's the downside of relying too early on language, right? I think one risk is, if you kind of relying too heavily and too early on language, it can just act as a shortcut, right? It will just compensate for the deficiencies in learning effective visual representations. And when your task is kind of simple enough, you might find this is okay. The problem can be solved by your favorite LLMs. But if you increase task complexity, if you get into the real world, you'll see our visual representations still kind of suck nowadays. All right, so I really want to kind of think about this, based on this comparison between language versus visual intelligence, right? There are definitely many very interesting and important tasks that require more kind of stronger language capability. But there are also many tasks that require more robust visual spatial understanding or visual spatial intelligence. So there's a lot of cool demos from OpenAI, from Google Gemini, and maybe giving you one example, looking at this whiteboard drawing of two cats. And the question is what does this remind you of, right? This is from a demo of Google's Project Astra. And it's indeed very impressive. The system can tell you, oh, this reminded me of Schrodinger's cat, right? But if you really think about this, right, it's not that difficult to identify there are two cats or what the shape is for the eyes. The truly impressive part is this knowledge association process to link this real input to this kind of very diverse and complex kind of knowledge that's encoded by language. But if you think about this, or through the talk today, we'll see more tasks. I actually require more visual intelligence here. For example, in some of the tasks requiring a visual search process, in this kind of embodied kind of exploration tasks, or maybe for some spatial understanding tasks. All right, before looking at these individual examples, let's just revisit the typical multimodal large language model pipeline, right? This is the framework that was introduced by Lava, but I think nowadays still pretty much the most popular approach to build a multimodal large language model. So essentially it involves a couple of components, and there's multi-stage of training. All these components include, for example, language model, the vision language connector, and also a vision encoder to extract visual tokens from the input images or videos, and to align this with the language space, right? So if you look at all these components, at least 2 years ago, people usually study a lot of different variants for the language component, right? Like people try to use better and stronger and bigger language models for this purpose. You'll have like better performance as well. And then there are like some key design decisions in terms of like how we can actually design the connector module, right, to align vision and language together. But for the visual token, tokenization of visual representation learning side, people usually just still use the clip model. And it's not just like a clip model, it's actually the original clip checkpoint released by OpenAI many years ago. So I don't think I need to like spend time talking about what clip is. But I think this actually leads to a key question that we looked into, I think roughly 2 years ago. Like we all know like clip is sort of like the best visual representation that we have, like the best checkpoint that we have for extracting visual information. But is it really good enough for visual representation learning? Or is it really good enough for to be used in a multimodal system? So there are like some cool examples from again from 2 years ago when we are trying to probe GPT-4V model, and we identified a lot of questions and images. They're not like tricky questions or tricky images or complex images. This is like really simple, straightforward questions on very simple images from ImageNet or Line dataset, right? For example, is dog facing left or right from the camera's perspective? Or in this example, is the edge of the heart in the picture white or dark colored? You can see like no human will make any mistake when answering these questions, right? But if we put these images and questions into the leading kind of GPT-4V model, you'll see actually the answers are completely wrong. So this makes us think, is there actually a systematic way we can identify this type of like examples? And maybe they will reveal some form of visual shortcomings of the multimodal systems. So the way we construct this, benchmark to curate all these examples and questions through this process of like finding clip blind pairs, right? So there's like a few kind of key steps. The first step is to find this clip blind pairs. So essentially we have like these two different spaces. One is the clip embedding space, right? And then another one will just use a visual self-supervised learning kind of space. So we want to kind of filter the data set and try to discover image pairs that are approximate in clip feature space, but distant in Dino V2 feature space. So that means like, for these two images, we know like clip cannot really distinguish between the two. But on the other hand, they are actually different, kind of images because, different, more vision-centric representation space, the two images, two data points are pretty far away. So now given this kind of two images, we can just ask human annotators to spot the difference between the two images, okay? So in this example, we can see, oh, the dog's head in the left image is resting on the carpet, while the dog's head in the right image is lying on the floor. So we can just like propose this multiple choice question, where is the yellow animal's head lying in this image? Option A, floor, option B, carpet, right? And by the way, here is, saying yellow animal because there's like another black dog in the background. So, but anyways, once you have this question and these choices, now we can just give this image, a pair of images, and also the corresponding questions and, the choices to the multimodal large model, and they will receive a score, only when both predictions for this image pair are correct. So this is like a very simple approach to get more examples here. And now we can see the results of the current multimodal models and also humans. In this comparison, we can see, like the leading systems back then, like China models, GPT-4V models, can perform accuracy around like 40%. And then like the Lava open source models like Lava, it's like even worse than random guess. But again, as I said, like for humans, these are like really, really simple questions and images, so you can easily achieve like almost perfect accuracy. So once we get these examples, right, and this really made us to think what is really going on, right? So we don't know, we didn't know, like, all these models from different companies, what kind of representation do they use, but it's reasonable to have this hypothesis, right? Like CLIP might be a problem here. And all these leading systems and open source models, they're all using kind of like CLIP models, CLIP representations as like the visual information extractor. So what we did after this is we just asked ChatGPT to identify 9 different visual patterns from this curated kind of samples in the benchmark. And then we can see, oh, there's like some questions about orientation, interaction, some questions about like maybe text or viewpoint perspectives. And now, like one thing we can do to verify this hypothesis is we can try to, convert this benchmark, this multiple choice question benchmark for multimodal system into a like image and text matching benchmark for CLIP using the same set of images and questions. So now we can see, there are actually indeed systematic failures in CLIP-like models, right? So like all this performance is not very good. It's below like 40% accuracy. But although like, for common benchmark like image and 1K, zero-shot performance, like the leading CLIP models can achieve already a very good performance, like 85%. And what's more interesting is it seems like CLIP failures and multimodal large model failures actually correlated, right? So in this kind of simple plot, we can show if CLIP performs poorly on visual patterns such as orientation, it is, then like multimodal large language model won't make a mistake either. So this is kind of interesting. This kind of like shows, we can, actually find these examples to really tell you actually CLIP model or like the visual representation component for the multimodal large language model system can still be a bottleneck. So in order to kind of like address this problem, this is just like one simple attempt. We can just use this mixture of features strategy becomes a pretty popular and pretty standard approach for building multimodal large language models. This is basically saying, oh, maybe instead of just relying on CLIP encoder itself, we can actually bring in another ring encoder, right? Like here in this case, it's very natural for us to just like add the Dino feature, side by side to the CLIP feature. And then like, with some carefully designed recipe, we can actually, utilize both representation. And this gives us like much higher accuracy for the multimodal question answering. So yeah, this is some of the results. But I think like, a quick takeaway from this relatively kind of like old work is I think visual grounding is still very important for language understanding and meaning, right, in this VQA setup. And only having good language representation is not enough because you need really a better grounding model. And another perspective is, CLIP has been here for too long, and that means like, there are like a lot of opportunities as well. And finally, I think, as I said, like maybe we had few successes for Vision SSL over the past like maybe 2 years. But I would say like this is still very much worth exploring. But maybe we just need fundamentally different ways to pursue the problem, right? Like maybe Vision SSL is still like very promising, but the way we conduct research and evaluate our research needs to change. We'll cover more about this later. All right. So quickly going to the next question. I think this is another very interesting question. So better visual representations, right? Beyond just static and global image feature extractors. So this is really motivated or inspired by this very native human capability of doing this deliberate system to visual processing, right? There are things, we don't need to pay a lot of attention, but there are scenarios that we need to really, go to search for some target real information to be able to answer questions, such as maybe finding the keys in this kind of cluttered desk, or like maybe, there's a question about this very complex diagram. We have to maybe first locate one animal here to be able to answer the question. So here's a very concrete example, right? So like maybe I'll just ask you this dumb question, like, can you tell me what's the color of the plastic straw, right? Yeah, you can think about this, you can look at this image, but the current system, right, like, if you only have a static and global visual feature extractor, what they will do is essentially they will do this kind of raster scan, right? They'll just like look at each individual pixel, and hopefully this will, cover the target target, and then give you the information you need. But like maybe for a reasonable, kind of human, what will be done is like maybe we'll see, oh, there's kind of like coffee shop. You're asking me about the straw, so I should like look at this place. There's a table. I don't see anything here. Maybe I move on to here. Oh, I actually see a few kind of like cups, and here I see the straw. And can tell you, oh, like the color is black. Right. So here is another quick question. For offline kind of talk, you really ask this as a quiz. I'll give you like maybe 5 seconds as well. Like, the question is, where can I buy this red mug? Right? So I don't know. Hopefully you can already see the answer. So if not, like maybe it's much easier if you can zoom in here. You can see just tiny bit of kind of Starbucks logo here, right? But this is really good enough for us to answer this question, and can see, oh, we can buy this from maybe a Starbucks store. But again, if you put this high resolution image into GPT-4V, which is say, oh, this mark in this image has logo reminiscent of Nuka-Cola. You can buy this from Amazon, blah, blah, blah. So, it's very evident like GPT-4V was distracted by this wallpaper here, which is showing, the Nuka-Cola like game saying, but then like, which leads to kind of completely wrong answer, right? But in our case, we actually built a new system, a new framework where we can actually answer these questions clearly. So you can buy this mug based on its logo at the Starbucks store or online at the Starbucks website. So how do we do this? So essentially, we just integrate this visual search model for multimodal large language models. And I'll skip some of these details, just give you some intuitive kind of like visualization here. So essentially, we don't directly want to extract the real information in one pass using like maybe one clip model or one dyno model, right? So, like this might be not enough, because if your resolution of the image is very high, if you, handling a very complex image distribution, you really need to just like, using your prior knowledge and then try to search for a certain kind of like cues to be able to answer this question. So this is like one example of this kind of visual search module. So here the question is like, like something about a guitar, right? And again, like this is a very high resolution and complex thing. So in order to search for guitar, like maybe the visual representation, models cannot really directly see the guitar, right? Due to like the resolution constraints. But what we can do is we can actually find this contextual cue, right? This is actually provided, by the large language model itself. We'll say, oh, actually the guitar is most likely to appear on the stage. This is a very reasonable guess, right? And now like we can see this heat map. This will allow our model to actually zoom in into this part. And then like we'll see this more target specific cue, because now we can actually crop this part of the image and now like do this visual search again. And finally, we can zoom in into the stage, and we can spot the target. And now like we can just put this information into kind of like visual memory, and then like we can rely on this kind of like cropped image, this found target, visual patches to be able to answer the question. So to me, I think this is like a general framework, right? In the future, I think there will always be two pathways for this kind of like VQA or multimodal understanding tasks. So one is more like intuitive visual processing. So you don't need to kind of spend a lot of compute for this. You don't need to do any search. this will be simple answers, right? So you can directly answerable through intuitive processing only, just like regular multimodal system nowadays. But now, like if you really want to handle this complex scenarios, think about like not just the high resolution image understanding, but like maybe for embodied tasks in the 3D world, or maybe for very long form video understanding. This like this question answering capability need to go through this kind of like consistent to deliberate visual processing pathway, where you will activate this visual search model and will write into this non-parametric and working memory, and then your final answer will be grounded in this kind of memory contents that includes maybe questions, the global information, the search targets, and maybe some localization information as well. So in order to as a proof of concept, right, in order to show this is indeed a very necessary task, we build this new benchmark called VSI-Bench. It's a vision-centric VQA benchmark with a lot of high resolution images from the SAM data set. And you can see, again, with this type of scenarios, the leading systems back to that at that time can only get to like random guess level performance. And some of these commercial chatbot models can achieve about like 50% accuracy. But our model, with a very small large language model, it's a 7B model, but with this, kind of visual search process, it can actually achieve much better performance. So the takeaway here is a good multimodal system should be able to, one, acknowledge that they cannot see, right? And like, by the way, right now it's not the case. So right now, I think for a lot of these models, even if they cannot see the information, they'll still hallucinate and just give you an answer, which is not what we want. And two, I think you need to have this capability of explicitly listing real information needed. And three, you need to understand and integrate the search results. And finally, I think this is related to kind of test time, scaling, which means like we really need to allocate more test time compute for more complex tasks. So we kind of faced a lot of like challenges from the reviewers from like 1 or 2 years ago, and people saying, oh, this is like, not as efficient as just like a simple visual feature extractor, right? Because you need to do this visual search process during inference. But I think like after OpenAI's O1, people now are much more open to this and also can agree, this test time kind of scaling is actually essential for this type of reasoning, visual reasoning tasks. And I would say like these are not really engineering hikes. Again, like it might be okay to address the problem in different ways for this high resolution image understanding tasks. But as I said, like, for this future, like multimodal future, right? Like where maybe we'll have like a lot of robots roaming on the streets, or we need to have like really have a great kind of analysis for very long form video. We need capabilities like this. All right, moving on. I think the next key question I want to ask is like, what are the necessary components towards building a better and vision-centric multimodal large language model? So this is a work that we did. We call it Cambrian 1. This was presented at Europe's last year. This is like a large effort that we want to also build a multimodal large language model by ourselves. But the focus here is, this keyword is vision-centric. So that means like, we kind of studied everything, all these core components in a multimodal large language model, except for the large language model itself, right? We just keep the large language model part controlled and fixed, but study the vision backbone, the, vision language connector, and the instruction tuning data and recipe, and also the evaluation protocol. Yeah, here, a few things. So the first thing that we looked into is the visual representations, right? So as I said, like, people usually just to try to use clip model as the visual representation in a multimodal system. We, brought kind of a Dino and some of this SSL representations into the system as well. But there are like many more diverse visual representations that we can use. So the question here is how we can actually evaluate visual representations and what visual representations to use, right? So we looked into like maybe supervised models, different self-supervised learning models as well, but also look at, diffusion model, depth models, and segmentation models. So overall, like we have like, I think 23 different models, and we have like this very comprehensive benchmark, which is like plug them into our kind of like multimodal large language model recipe, and then like, evaluate their performance on all these VQA tasks. So to me, I think this represents a very interesting, kind of paradigm shift if your goal is to evaluate or make progress in visual representation learning, right? I said this in the very beginning. Before, for visual representation learning, we have this pre-trained models, we have this evaluation protocol, linear probing or end-to-end fine-tuning, and then we have this benchmarks, the standard recognition tasks. But now, like if you think about like multimodal large language model, this is also a very good way to evaluate the visual representation capability, right? You still start with a pre-trained vision model. You need a connector here to align this with language space. That's fine. But then like instead of just doing linear probing or end-to-end tuning, what we can do is we can just perform this visual instruction tuning with a large language model, right? So this allows us to move beyond all this kind of like traditional standard benchmarks, but be able to, benchmark with all this very diverse VQA tasks shown here. And arguably all these VQA tasks are actually more kind of real world. They are more noisy, but they are kind of flexible and kind of interesting for many of these real world challenges that we face. All right, so talking about like evaluation protocols, there are like so many benchmarks for multimodal large language models, right? So one problem I already have is, look at all these papers and all these announcements from different companies. People will just, list 20 different benchmarks and maybe an average number, right? But then like this is really not ideal if we want to systematically evaluate a multimodal large language model and interpret the evaluation results. So the first thing that we did is, we just have this kind of meta level study to look at all these benchmarks, right? For example, we look at who's answering the question, the large language model or the multimodal large language model. You can see for some of these benchmarks, enabling the vision component or disablling them doesn't make a difference, right? That really means for some of these benchmarks, even though they are multimodal benchmarks, they are still like very language centric, right? That means like your vision part doesn't really, play a role here. Then like in our case, in our vision centric study, we want to at least, make people aware this problem exists. And then like what we can also do is to group all these benchmarks by certain kind of like correlation across all these like models that we're on. So now we can see there are like different clusters of these benchmarks. We have general benchmarks. We have some benchmarks that's really about knowledge, like maybe math problems. There are also like some benchmarks that's really just about OCR and chart understanding. And there are like small kind of representation about like vision-centric capabilities here. So this is like the vision-centric kind of benchmarking is really tiny compared to many other capabilities. So the question is like, how can we actually scalably generate vision-centric multimodal large language model evaluations? Our idea is we can actually repurpose existing vision benchmarks. So we call this the CV-Bench. The source of this benchmark is from this standard, vision benchmarks like 8020K or MS COCO. But what we can do is we can just like, convert them into this flexible, VQA questions. So we have this 2D spatial relationship challenges, or like object counting tasks. And also in 3D, we can probe models' capability in understanding depth ordering or relative distance. So now like we can have like about like 3,000 manually inspected examples added into the pool. This is still like not as large as some of these other benchmarks, but this is already much better for us to evaluate the vision-centric capabilities. Now, like we study, instruction tuning recipe, I'll be like maybe more like faster here, and just tell you a few kind of takeaways. For example, in this two-stage of like instruction tuning, model alignment data definitely helps. And also unphrasing the vision backbone, right? Unphrasing the vision encoder definitely helps as well. Of course, the downside is like the training will be slower once you unphrase the vision encoders. And okay, like this is like the most important like, figure in our paper, which we really compare all these real representations across this buckets of evaluation tasks that we designed in our paper. So you can see a few kind of like interesting conclusions here. First of all, like I think language supervised models are still the best. This is represented by all these kind of green, bluish curves lines here, and notably, Siglib model from Google is still achieving the best performance across the board. But you can see actually the gap is largest in OCR and chart, right? So on other categories, I think it's roughly fine. Like the gap is there, but they are like very small. But for OCR and chart, this is like huge. But if you think about this also makes sense, right? Like when we're training all this vision-centric, SSL models, we'll not use like OCR and chart data, right, in the data kind of pool. And like if you haven't really seen data like this, it's kind of expected the performance will not be very good. So I think this is also like one interesting insight we can only get once we have like this more kind of fine-grained categorization of the benchmarks rather than looking at the whole thing or the average only. Okay. And the third thing is like confidence are still like quite good. Like the confidence model we have here actually very good at OCR tasks. This just says, like confidence is by design very friendly to this high resolution images, and it's like performs like very well here. And then like looking at the best SSL models, which is Dino V2 model here, you can see actually the model is pretty good at vision-centric tasks. Actually outperforms many of this kind of CLIP-based language supervised models. Still worse than Siglib model, but the gap is like very much small. Okay. And then like talking about real representations, I think training with more data also narrows the gap between language supervised and self-supervised models. Okay, so here's like a little bit of a sneak peek, right? Like we identified all these issues. We can show actually there's a huge kind of data gap between the best SSL model and also like this kind of like Siglib like language supervised models. This is just like a sneak peek. The paper probably will be out soon. So we're trying to have like real SSL 2.0 paradigm. We will actually try to bridge this data gap and also like the model size gap here, right? So before we're only looking at data, smaller than 1 billion samples, and models smaller, also like smaller than 1 billion parameters, and we're just using the standard evaluation benchmarks. But now we can do data scaling, we can do model scaling, and we can also have more evaluations. And one, again, spoiler here is once we actually bridge this data gap, right? If we can actually use the web scale data to train this SSL model, for example, the Dino V2 model here, we can see actually, you also exhibit a good scaling behavior. This accuracy shown here is the average accuracy across these four different categories. And you can see, but just like having more data and larger models, we can have like very big improvement here with the SSL model as the real representation for multimodal system. I'm happy to discuss more about this once the paper is out. All right. So we also conducted some other studies like, connector design. We don't have much time here. I'll just like skip this. And, like spatial inductor bias is very important here for OCR and vision-centric domains in this connector design. And finally, we did a lot of study for data. Actually, I think this is the kind of like good instruction tuning data for multimodal systems. A lot of other papers also use our data, but essentially we collect all of the kind of like viral instruction tuning data from online and process them, and then did some data balancing and data mixing ratio study as well. and we can see actually data quality matters as well. So as I said, like this is like a comprehensive, kind of exploration in the space, and of course, in the end, we achieve, some form of kind of sort out performance compared to other models. But have a quote unquote unsold out here because our main purpose here is not really, propose yet another state-of-the-art multimodal large language model. The real takeaway here is, like it's really good that we have all this flexible evaluation strategies and, like this multimodal large language model, visual instruction tuning allowed us to have a like different way to evaluate the visual representation learnings. But we need to consider many kind of like, behaviors of the model, and we need to do this science properly rather than just, running a lot of the models on a lot of benchmarks. So I think this is something I hope the community will also follow. But anyways, so that concludes this question. I want to kind of like talk about like one more question in this kind of multimodal understanding part. And this is maybe more relevant actually to the group of people here. So this is some like new kind of research that we did in understanding, exploring how multimodal large language models, we call it think in space. So I think in computer vision, we definitely study space, right? And usually in 3D, but not really about thinking, right? Like, if we talk about like the ScanNet challenge, sometimes like at least in the current benchmark, we study like maybe segmentation, semantic segmentation, detection, and so on. But there's no kind of like, language-based reasoning tasks there yet. And also like for, all this video benchmarks, right? We definitely study thinking, right? For this video MME benchmark, we study how the large language model can reason over like maybe a long form movie. But usually they are not done in space, right? Like, we're talking about like video understanding, but videos are also like very different. Some videos are more sequential, it's more like storytelling. That's more maybe closer to the language understanding part. But some of the videos are more like maybe vision-centric. So this is we call like real spatial intelligence, and this is something psychologists and cognitive scientists actually study for a long time, right? This is a famous example of this mental rotation task, right? Like given one variant here on the left side, and you want to, answer which like rotated, copy here is the same object to the left one, right? And I think this is like a key intelligence or intelligent behavior for humans. But the question is like, can multimodal systems also have this capability? Like maybe as a more down to the earth kind of like example, right? Imagine you are going to a furniture store, you look at all this and you try to, think about like your own apartment. And as humans, right, like we watch these videos, like this always on live streaming videos, and we can conceptualize them in spatial terms, right? And this is how we know if the sofa that we, want to buy, can it fit in my room? Like how do I kind of position it? And does the color match like maybe some other furnitures? We can discuss a lot of this. And a lot of times this is really go beyond like, verbalized reasoning process, right? Like, you will have just this mental imagery, and this allows you to perform a lot of tasks very efficiently. So again, like another example here, the goal is to, watch the video, answer the question, right? Questions like how many coat racks are there in this room? Yeah, this is actually a very long video. But I think you already have a very clear understanding of the space right now, so I can pause here. So I don't know what your answer is, but my answer is 2. But then like if you really, put this video to Gemini 1.5 Pro, it'll give you a wrong answer. Oh, let's just say, oh, there's only one coat rack. There's another example. This is a little bit of a long video. Let's just like watch it together. So the question is like, if I'm standing by the nightstand, you can see the nightstand here on the side of bed, and facing the chair is the closet to the left or the right of the chair. Right? I'm gonna repeat the question. If you're standing by the nightstand and facing the chair. You don't see the chair before, but now you see the chair, right? Standing the nightstand, facing the chair. Is the closet to the left or the right of the chair? Okay. Again, you haven't seen the closet yet because again, this is quite a long video. I actually maybe you are very familiar with this video because I think this is one video from a ScanNet. All right, after a few seconds, now you can actually see the closet. Okay, so maybe you can provide your answer. I don't think this is like very complicated question to answer. So ground truth is A, to the left of the chair, right? But again, like for Gemini 1.5, the best kind of like video understanding model will give you a wrong answer here. So we studied this problem in this paper, just accepted as CVPR 2025. It's called Thinking Space, how multimodal large language models see, remember, and recall spaces. So we construct a lot of like this benchmarks and tasks. And again, they're structured in this VQA setting. And one really kind of interesting thing that we did is all this annotation process is facilitated by the 3D reconstruction datasets. And thanks to your group, by the way. What we did is basically we repurposed existing 3D reconstruction datasets like ScanNet and ScanNet++, and also ArcSyncs. And then we can actually, primarily auto kind of annotate a lot of these QA pairs using the bounding box annotations from all this 3D reconstruction datasets. But of course, we have like some human in the loop to do this quality review to ensure the benchmark correctness. But this is how we can actually get about 5,000 different questions covering different capabilities in multimodal kind of spatial reasoning and understanding. So looking at the results, right? Again, for humans, this is I would say like definitely not a trivial task, right? This is not like a simple thing that you need to think about. You need to kind of watch the video and maybe like multiple times, but you'll get there, right? This is basically from our human annotators. They can achieve very high numbers. For some of the tasks, it's about like 90% accuracy. But some tasks, in average, I think it will be like around 80%. But again, like with the leading model like Gemini 1.5 Pro, the average performance across all these tasks will be less than 50%. Okay. Again, if you look at this open sourced video language models, even with this kind of like the best 72 billion language models, so the performance around like 40%. So this is like really far from the human level performance. So we did a lot of error analysis. You can read our paper to learn more. Essentially, the takeaway here is the spatial reasoning, not like linguistic capabilities or like maybe perception capabilities. Means like, they can definitely identify object categories. This is like the model has no problem with it, but the spatial reasoning capabilities, the main bottleneck for multimodal large language model performance, our VSI-Bench. There are like also like more interesting takeaway here. For example, a lot of like this existing language prompting techniques like chain of thought, which actually works quite well for kind of like video MME, like traditional kind of video understanding tasks. But in our case, right, if you need to perform some spatial reasoning, it seems like this linguistic prompting techniques, although effective in language reasoning tasks, are primarily harmful for spatial reasonings. So again, in some of these figures, it's more like the more you think, the more mistake the will make. Another very interesting thing is, it seems like the model has this really local word model. So essentially, we ask the model to generate this kind of cognitive map from this multimodal large language models, and we can see when remembering the spaces, a multimodal large language model actually forms a series of local word models in its mind from a given video, rather than a unified global or 3D model. Right? It means like, if the question is about maybe two objects in near kind of frames, or if it's just like a question that can be answered by looking just like one frame, then the model performs really, really well. But if this is like long-form kind of reasoning task, where you'll observe one object, but like then the question is about like another object, but after many, many frames. This requires some form of unified global word model, but unfortunately, the current model doesn't have this. So the takeaway here is the video understanding is easy, but thinking in space is hard. Again, like I'm really looking forward to more discussions with your group here, just because I think this actually has a lot of cool implications for 3D vision and representation learning research, right? Like I think it's like very promising direction to explore how we can actually, bring all this 3D priors, all this maybe reconstruction research, and novel video synthesis research, and make them useful for not just like giving us nice looking pixels, but also for video-based multimodal understanding and reasoning tasks. All right, so maybe I can spend like maybe 5 more minutes and talk about like the multimodal future and some of like this open questions. Like I'll be very quick here, but I think there are like a few directions I'm also like pursuing right now. Like first one is maybe unified multimodal modeling, and related to that, I think it's very interesting to discuss the synergy between representation learning and generative modeling. So we have probably already seen this, right? Like this experiment with Gemini 2.0 model, like this native image generation model capabilities, and how this actually enables, really good, unlocks new capabilities for image editing, subject-driven, generation. But I think this really tells us, right? Like in the future, generative model is not just like generative model on its own. You need to like intelligent engine behind it. So this will be very crucial to unlock many, interesting applications like, the Gemini 2.0 shows. So for generative models and representation learning, this is kind of 2 directions, right? Like first direction is, can we leverage generative models for representation learning? There are like recent papers show that like diffusion models are okay-ish representation learners. We also have a paper, let's say in iClear this year. It's about deconstructing denoising diffusion models for self-supervised learning, right? There we actually identified a few kind of key insights in making, a denoising diffusion model a good representation learner. But still, I think in general, like the performance here is like much worse than the leading kind of self-supervised learning models. But I would say like another more interesting direction is about representation learning for generative models. So I think we're all familiar with DIT or SIT. We have the scalable architectures for diffusion models, and we can generate this very nice looking pixels. But one of the problem is usually for this, like let's see a DIT or SIT X large models, this in order to achieve this kind of like state-of-the-art performance regime, this actually takes few weeks to train, right, on a lot of like GPUs. So we have this new work, again, published at iClear this year. We call it representation alignment for generation, and training diffusion transformers easier than you think. So this is based on really one really interesting observation by looking at the representation alignment of a diffusion model and some of this best self-supervised learning models like Dino V2, right? I think you can just look at the third figure here. This just shows like, through the course of training, the latent representation learned in this diffusion transformer is getting better and better and more aligned to the, kind of like best, SSL visual representation here. But it seems like this process is like very slow. If you just train the model with a diffusion objective, it kind of struggles to get there, right? It seems like the representation definitely matters here, but only with diffusion objective, the model can do something, but it's like very, very slow. We use like this CKNA metric developed by this Platonic representation learning paper to measure the alignment here. But then like, in order to address this problem, we propose this very simple regularization approach where like, when training a diffusion model, right, instead of just having one string, like, denoising neural network, we just take one of the intermediate layers from this diffusion transformer block and then add this regularization loss to try to align the representation from this lower layers of this diffusion transformer block and align it with a pre-trained variant encoder's representation, such as using DynoV2. Okay, so the hypothesis here is diffusion models must first establish a very strong representation before rendering the final pixel output, and diffusion loss itself is not good enough for this purpose. So after we do this, we can see this actually works, right? So after you have this regularization for representation alignment, indeed you can have like better alignment to the leading target representation like DynoV2. But what's more interesting is this makes your diffusion model training much more faster, right? Under this setting. With a DIT or SIT XL model, we can have like 17.5x faster training convergence compared to the baseline. Here are like some more visual conversions, results. And there are like more quantitative results as well. And then we can also show the scalability of REPA. This regularization loss is also very good. You can enjoy more benefit of this representation alignment loss using a larger diffusion transformer. And now this is not just about convergence. REPA also leads to better generation quality across all this benchmarks. And also recently we find this is also helpful for text to image generation tasks. All right, so the final takeaway here is I think generation for representation, this is still promising, but not much success yet. For representation for generation, this seems extremely important. People realize this in recent few months. And finally, I think I would say scalable visual intelligence still a very open question, and scalable visual representation learning is definitely a key here. All right, so I'll stop here and thank you. I'm happy to take more questions.
Cool, thanks so much. Any questions? Just unmute and ask. Okay, I can maybe start with one question. So I'm curious about obviously the spatial understanding is super interesting. So I think when it comes to representation learning, how much do you think is actually in the representation as kind of a spatial / 3D scene layout, or is it more oh, it just maps to some, I don't know, kind of more like an unstructured graph, and then it gives you still kind of the right answer, kind of what an LLM would do in a sense? Or do you think there's actually some 3D structures forming as part of the underlying representation at the end of the day?
Yeah, I think this is a great question, but also a very open question because I honestly I don't know. I feel like this should be very promising. In a sense, we have early preliminary evidence that relying on language model itself, I think this is not going to be enough. You can imagine maybe you can have this two-stage system, right? Maybe you can output the scene graph, some form of scene graph first, and then let large language model to operate on the scene graph to tell you everything. But this really doesn't work, right? I think people work on this for a long time. It's equally kind of hard problem to generate this type of structured scene graph. To me, I think the more promising approach is to try to make it more end-to-end system. We can inject a lot of 3D representation, maybe priors into this instruction tuning process, but this has to be latent process. Yeah, I think only relying on this more agent type of a strategy and hope the large language model can solve everything. Based on our preliminary experiments, I think it's not going anywhere. Yeah, that's my feeling right now.
How much do you think, this was actually one question on YouTube too, how much do you think should be part of the architecture in itself? Do you need some sort of 3D operators or anything related, or even 4D operators, right? If you go to dynamics eventually. Or do you think it's mostly okay, existing architectures, some sort of transformer-based architecture is good enough and that's it? Or do you think we have to still change that?
Yeah, personally, I like transformers. I don't see a huge problem about it. But I think when we're talking about architectures, like there could be different, things that we mean by architecture, right? Like, I think it can still be a transformer architecture, but then like maybe this architecture need to be, like you can think about like maybe some other different ways to utilize maybe a 3D representation and inject such information to the transformer. There could be like maybe a modular design, maybe you have like maybe some 3D reconstruction architecture as well that can nicely kind of integrate it in the whole system. I think this is definitely possible. Yeah. But again, I think this is a really excited kind of a direction that I don't have an answer yet.
Yeah. Another question on YouTube was basically how much, or like, do we know how related this is to all like cognitive sciences, basically? I mean, in a sense, like how do humans do it versus like how do LLM/MLLMs do it? Is there anything known? Is there any insights that we can still leverage as a community there?
Yeah, I think a lot of cognitive scientists are actually, trying to bring all these inspirations from psychology and cognitive science to like maybe large language models and probe the systems. I think like there are a lot of like fun, kind of like examples and all those behaviors that people discover. And with respect to this 3D kind of reasoning stuff, I think I was just like chatting with Leo give us the other day, and he mentioned like very interesting kind of a psychology study for people, right? Like in terms of like perspective taking, right? So he says like some people are naturally very good to align like a map to the kind of like real direction. So it's almost kind of like O1, access time, so people can know which direction to go. But for some people, you kind of need to do this kind of in a linear test time scaling fashion where you need to like maybe rotate your map and then you know where you want to go, right? I'm definitely the latter. I think maybe with Google Maps, people are becoming more and more stupid about this. But one observation from kind of like interacting with our human annotators, which are kind of student volunteers, by the way. I think basically, I think people can be easily trained to do this and perform this well. So this is like not trivial tasks. From the beginning, they will be confused. Like, what do you mean? Like, what information should I look at? But then after a few questions, after watching these videos a couple of times, they can adapt very quickly to give you like very accurate answers. I think like the current model doesn't have this capability, right? If you upload one video to like Gemini or whatever, it won't know like you can actually condition on your question and maybe look at specific part of the video, and all those are like not there yet. But again, I think this will be very important things to have in a multimodal system in the future.
Okay. Any other questions in Zoom? Okay, there's so many questions on YouTube right now. I can't go through all of them. Okay, another question is basically, what role do you think the 3D priors are going to be based on video-based multimodal understanding?
Yeah, so I think we definitely need to have the 3D prior, right? Essentially, for humans, also just like look at videos, right? Like we don't have a 3D reconstruction of the world. But like, in our brain, we kind of have this 3D prior, so we can easily reconstruct things. It won't be kind of like perfect, kind of like high fidelity reconstruction, but it will be something that's kind of useful already. But again, like looking at this, I think how we can actually, connect this kind of longer form video into a reasonable 3D kind of like prior, or utilize 3D prior to build kind of 3D reconstruction that's good enough for reasoning tasks. I think this will be definitely a frontier research topic. Yeah, my take is like it's definitely going to be very important. Yeah.
Cool. Thanks so much. So I think we're a little bit over time. So thanks everybody for joining. I'm gonna end the stream here now. Thanks everybody from YouTube. And yeah, obviously check out Saing's cool stuff. There's a lot of cool stuff coming out. Really exciting area, obviously. And there's definitely more to come. So thanks a lot.
Thank you. Thank you, YouTube.
All right. So YouTube is out.
Cool. Yeah. Okay.